Welcome to Manimated AI. In this video, we will uncover how eigenvalues and eigenvectors power one of the most fascinating ideas in AI, eigenfaces. You see different versions of Alex, but no matter how he changes, your brain still knows it's him. Let's now understand how computers see your face. This is just a grid of thousands of tiny colored squares called pixels. Each one stores brightness. To simplify, we remove color. In grayscale, each pixel just holds a brightness value from black to white. We then flatten the pixel values into a long list, a vector. This is how a computer sees your face, as numbers. We saw that after grayscale, we get numbers. But now the question is, how do I figure out what really matters in all these numbers? If we compare lots of faces, we start noticing patterns. Some features matter more than others when telling people apart. Every face is a little different. We start seeing features like face width, eye distance, or smile height. Each has a unique type of difference between faces, like wider vs. thinner faces or brighter eyes vs. darker eyes. When we do this, we notice that the points don't scatter randomly, they tend to spread in certain directions. Those directions, that's what the computer looks for. Let's get back to our Alex example. We want the computer to learn what changes the most across all faces and what patterns make each face unique. The computer looks for the directions where faces differ the most. These are the most important patterns. Each of these directions becomes the foundation for a special kind of face, an eigenface. Now let's talk about eigenfaces. Each face, once image is converted to numbers, becomes a point in a huge mathematical space. This space can have hundreds or even thousands of dimensions. For simplicity, we're showing it in 2D here, but these face points don't scatter randomly. They stretch out in certain directions more than others. Those directions are what the computer cares about. These special directions, which describe the most significant ways faces vary, are called eigenvectors. So now we know eigenvectors show the directions of change. But how important is each direction? That's what the eigenvalue tells us. The eigenvalue tells you how important that pattern is. A big eigenvalue means a lot of faces differ in that particular way. Patterns with small eigenvalues don't matter much, so we often ignore them. So what do these most important directions look like? They look like blurry faces. We call them eigenfaces. Each one captures a unique type of difference in faces, like face shape, eye distance, or mouth expression. These aren't actual faces. They are the building blocks computers use to describe real ones. Okay, imagine this. We start with just the average face. Pretty boring, right? Kind of like a blur. Now let's mix in the first ghost face. Aha, you see some details show up. Add another and it looks clearer. With 5, 6, 8 eigenfaces, suddenly boom, it's Alex. His face comes back piece by piece. It's like snapping Lego bricks together, except each brick is a ghostly pattern of a face. That's the magic of eigenfaces. So, to put it all together, eigenfaces work by reducing every face to a set of patterns, the eigenvectors, weighted by their importance, the eigenvalues. In practice, this means a face is no longer just an image, it becomes a compact mathematical description. And by comparing these descriptions, the computer can recognize not just a face, but who the face belongs to. Eigenfaces allow recognition by reducing a whole face image into just a small set of numbers, making matching fast and efficient. Instead of storing thousands of pixel values, we only store the weights, compressing memory of each face. Eigenface methods were early foundations in security checks, like ID verification and passports. Eigenfaces marked the first big step in teaching machines to see and recognize us. You've built the tools: vectors, matrices, transformations, and eigen insight. Now see how far they reach. Here are 3 real-world challenges. For each one, ask, which eigenvectors define the pattern, and which eigenvalues tell you what matters most. In vibration analysis, vehicles vibrate across modes, modal analysis isolates them. In sports analysis, teams blend skills, dimensionality reduction highlights what drives wins. In facial recognition, faces vary with light and pose, eigenfaces stabilize identity. Pause the video here and think for a minute. So tell me, what will you build with linear algebra? Share your approach in the comments. When math meets intent, systems change. I can't wait to see what you build. Thank you for watching. Don't forget to like, share, and subscribe, and we will see you in the next episode. Stay tuned. This video is made by Joshi. Keep learning, and I'll see you in the next video.